So here we go. Let's listen in. Yeah. Yeah. Huh. Okay, that's good. I'm relieved. We are just waiting for the Rocket Lab to go live stream with their stream. So let's go. Yeah, nice. This is what I want to hear so far. Okay, even for my audio loop, it's also good. So let's go in. Hello, everybody, and good afternoon. At least my place right now, it's 12:31:20 p.m. here in Sarawak right now in Borneo. So hello, everybody. Let's start with my trademark here. So hello, everybody. This is Daniel Suguwa, and today is my 60th live stream. So we are going to watch the launch of the Rocket Lab's Electron rocket that will carry the STP-S30. STP stands for Space Test Program. Yeah, that one is also this one will be launched for DiskSat demonstrator satellite there. Pretty new here. This one, from what I know, this is a collaboration work in between USSF, United States Space Force, and also NASA. We are going to see the launch of it. So, and because this is a collaborative, so this is sort of partly a civilian and also partly a military mission satellite, but in partnership together, because of course this both side will actually going to use the same design and the same things and what's on. So that's why it's very important. Okay, so I've already reset this position a little bit. So that's why we are going to see here. And I believe that because of the partly this part civilian mission, we might see this up until around T plus could be 55 minutes, almost an hour, and then after the deployment we shall see the result. Okay, and also there's some more interesting stuff I know about about this stuff, also reading based on my on some of my reading on the articles, and also on one research paper that's also being how do I say, that's also, yeah, that's my phone ring a little bit there. Don't worry about this slight notification. And yeah, and also that research paper in particular that details about the DiskSat mission there, that one also details out about specifically what's the rigidity of the satellites, what's even the total mass, and some breakdown, despite not really the most how do I say, not the most easiest for my reading, but it's okay. At the end of the day, I'm not an aerospace student. I'm a computer science student, but I do understand some part of it. What does it say? So we are also going to go together with it as we are waiting for the Rocket Lab to go live. Yeah, still waiting. Rocket Lab is still yet to go live. They should be live around 20 minutes before the launch. So that's it. Why not we go together together for this stuff? So let's see. I want to see, where do I want to start, because it's a bit hard. A bit hard, tough sell for me to know what we are going to go first. I guess maybe something more like we go with this paper that's also being that's also distributed on the 36th annual small satellite conference, which let's try see from my search first, okay, before I switch this source. I don't know what's happening. Maybe, yeah, maybe I need to adjust a bit of my keyboard. I mean, you don't hear it, but it's okay. Okay, which was how do I say, which how do I even translate this properly, huh? Which was presented on 36th annual small satellite conference back in 2022. Yeah, specifically on August 2022. So I'm going to get us read a little bit while we are still waiting, which it's going to launch around more or less around less than 24 minutes from now. So okay, so let's go here. Okay, so here's the paper, and fortunately it looks like it's not entirely up there. Yeah, so let's go together with this paper, this one, the DiskSat demonstration mission for a two-dimensional satellite architecture. So I'm not going to read too much here because guess what, it can be a little bit dry and boring if I just read it straight away, and I don't want to be that kind of person to describe to you what's happening here and there. So let us go some of the key detail points here, what this DiskSat satellite is going to be. And yeah, this one is it describes itself as a quasi two-dimensional satellite, aka there's another name, 2.5D. Yeah, especially if you're a computer science person like me, we not really, not super relevant. It's more like, yeah, even if you even heard about the technique of 2.5D graphics, it's sort of like that. It's like combining, it's like a sort of hybrid in between 2D flat surface and also the 3D, where there is like 4 degrees, I don't know, 6 degrees touch of feeling, something like that, about the graphics one. But this time it applies on the satellite. The DiskSat here in particular, from what from my reading, is that it has like a 1 meter solar panel. No, it's a 1 meter in diameter, and it has a thickness of 2.5 centimeters. It's pretty thin as it can get, you know. Just like if you're trying to buy a gaming laptop, you try to cram together. So that's basically their mission. Instead of trying to make it looks like a desktop, they want to slim it down to a very good, decent gaming laptop thickness, with a good battery with a good power consumption, energy density here and there. Because from my reading also, the volume itself almost like 20 liters, which equivalents around 20 CubeSat, around 20 units of height. Should be translated around 2 meters of the height if you try to translate it on CubeSat. Okay, and the structural mass overall, just to build it, is actually less than 3 kilograms. But if you try includes everything, including the solar panel, and also I believe some fully loaded propellant inside it, engines and whatnot, and also for the attachment to be attached on the payload adapter dispenser, it will be around 10 kilograms or less, slightly like that. So that's why I have already do a little bit of calculation, because it's they are going to launch around 4 DiskSat satellite demonstrator, right? So 4 times by 10, it's obviously going to be 40 kilograms. Quick math, some people says, and especially if you get some of these reference, you might know. Okay, but enough diverge with all of this with talk here. And from And yes, from if you see on the paper, they expected to launch last year in 2024, but instead it's almost 2 years. Yeah, originally they set this for early 2026, but they expedite the launch of this to this late 2025. Yeah, this this Christmas season, I guess. And yes, I'm going to change that background. Usually I'll use for my video soon enough, when we are going on the winter solstice, I believe that's where I'm going to change it officially after that. and and yes, and it says here it can actually host a 200 watt of solar cells. Yeah, the power of the 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 power of it with that can be supplied around, if I remember, 5 volt or 10 volt. And inside of 200 watt like that, it has like some backup around 50 watt, something like that. It has like multi redundancy in case anything happens with one of the power supply. It will and also batteries, it will just change to another. I mean, like, it's a very very smart idea to begin with. And it's going to be operated around the very low earth orbit, which actually would be around, starting at the very low 150 kilometers. Usually the lowest I can find up until the 400 kilometers region. So that's what they're going to do. But on this mission, Rocket Lab will specifically going to target the launch itself to the 550 kilometers at the mid-inclination orbit around 45 degrees. Yeah, so pretty good number to go. Yeah, and for now they are going to stack 4 DiskSat, but in the future they are going to go with 20 DiskSats for it. Okay, and I'm not going to go too long. We will actually going to skip over something that's not very 100% interesting, and they just say like, oh, because it can be made small and still rigid, but while still keeping it lightweight, you can actually cram whatever instrumentation inside it. If I remember correctly from my reading, they can actually cram it around 3.5 kilograms of instrumentation, telecommunication, and what's on inside of this. Yes, this one, from the reading here, structural mass of the disk set itself is actually lower than 2 kilograms, but so they said that to keep the entire bus mass, for example, their power supply, ACS stands for altitude control system, and also other avionics, under 5 kilograms, it says, should not be a challenge. Okay. And even if and even if they want to host how many payload inside they're like attached together, like 5 kilograms, it's still going to be under 10 kilograms of the total satellite mass there. That's why I used the figure around 10 kilograms just to be safe. Okay, so we assume one disk set going to be at 10 kilograms. And yeah, not really super duper interesting. Yeah, and also because if you want to know, that very low Earth orbit region, according to this paper and also from my reading, actually is one of the least utilized area for the satellite, because you need to know, even though the atmospheric drag isn't as big as us here on Earth, and also especially around the aeroplane area, it's still in terms of space related stuff of the atmospheric drag, it's actually way bigger than if you try to go upper up there, like typical low Earth orbit around maybe 500 kilometers, 600, or even if you want to go higher, you can go with the MEO. The medium Earth orbit should be around 10,000 kilometers and upward, something like that. Yeah, 10,000 kilometers until around until around 20,000, and then afterward it will be stationary of orbit around 30,000 kilometers up until translunar orbit, something like that. Yeah, and because of that atmospheric drag, of course it will require significant amount of delta velocities. Well, basically just another way to say that it needs to go in certain speed. Yeah, even though velocities and speed is not 100% accurate, but I'm using very layman term here to make you guys understand. It needs some amount of speed and also acceleration needed to just keep it going, so it can stay around that boundary area. And from another reading from I can say, yeah, and also this one, the one that actually builds this is the Aerospace Corporation, the same organization and agency that actually also provides us with data about the re-entry, the satellites re-entry and what's on. So this is the same one, yeah. And this is how it looks like on the DiskSat demonstration satellites there. There's the gap for stacking if they want to clamp it down there. Gap for stacking. There's also solar cells, solar panels, essentially, avionic bay, whatever it needs, and also electric thruster there. Yeah, so electric thruster, it can be anything. It could even be a water propulsion. Yeah, and also because you want to know, water propulsion, technically you can say one of my favorite research part, so to speak, especially if I want to learn something like that. And also about xenon, whatever whatever propellants needed. This one is actually one of my personal research interests. Yeah, even though I learn about computer science like that, and also out of that scope. And there's like 4 primary objectives of this project. There is number 1, to develop a DiskSat container / dispenser capable of supporting the DiskSats during launch and of dispensing the satellites one at a time once on orbit. And number 2, obviously, develop a DiskSat bus. Number 3, to demonstrate the operation of the DiskSat dispenser and bus in orbit. And 4th and finally would be to develop a first draft of a DiskSat standard based on lessons learned in developing and flying the dispenser and bus, which this mission actually going to aim for. That's why this technology demonstration is very important. And yeah, and also at some point, initially it will go to 550 kilometers of altitude, but eventually, out of these 4 satellites, the two of the satellites will actually change the altitude to a very low Earth orbit, VLEO, around, if I remember, around 300 kilometers. Yeah, around 300 kilometers and below. And another one, another 2 satellites will actually just change latitude or maybe inclination, something like that, to demonstrate how it actually works. Okay, so that's that. We are not going to bore you guys with this. You are not going to understand this. And even if I could understand, it's a little bit hard how to explain this in very layman term. But in the nutshell, in the nutshell, one of the material that they are used for the satellite structure is actually composite. It says here it consists primarily of a circular rigid plate that was fabricated as a composite sandwich with graphite / epoxy face sheets, and also an aluminum honeycomb core. So this is very important here. I've already highlighted there. And yeah, another reason is very simple, because they want high strength to weight ratio. and also low coefficient of thermal expansion, aka it didn't expand too much on any thermal condition, so it can still keep its shape pretty well. So that's why, and hopefully if you're a material scientist, whatever, that watch this stream, I hope you guys can correct me if I'm wrong, but this is my understanding about this topic. And this is even the simulation. You can see this deflection under the static load, especially if it's going under the highest peak of stress around 42.3 Gs of static load, aka around 42.3 the times of the gravity of Earth. So if we try to go with my calculation, it's not going to be that long. 42.3, if I remember, it's around 9.8 usually meters per second of gravity's Earth. It will be around 14.54 meters per second of acceleration, around already a speed of sounds of gravity pull. Wow, that's already pretty high stress load there. They are testing out using this computer simulation. Yeah, CAD, computer aided design. It's still pretty useful till this day, but here. Okay. Oh. Okay, I'm sorry, we have a little bit of dropout, but we solved it promptly, just in time before the flight. Okay, nice, we are back again. Okay, and also it says here, fixed ages, 6 degrees of freedom, 4 PLCs, something like that. And speaking about degrees of freedom, yeah, well, statistic stuff. I mean, it's still a pretty useful knowledge, but yeah, it is what it is. I'm not going to go too long. You can see there, central chassis box, represented by 5 kilogram point of mass there, and also a propulsion unit 1.45 kilogram point mass. So even if you try to add this all together, it's just only around 6.45 kilograms, not including other kinds of payload, but they still can do this under 10 kilograms. And this is how it looks like, the preliminary avionics layout. There's the antenna, pretty compact. I mean, even if you learn about the communication stuff, even just slightly, as a computer science student, why is it. And also reaction wheel, so it can actually change the direction of the satellite without using any propellant, supposedly. And also there's battery pack, of course, pretty typical. Yeah, altitude control. Oh, and also apparently they are going to use the aero cubes as the propellant here. Okay, there's some torque, momentum, storage capacity. Okay. So for this mission, if I remember, they required around around the delta velocities of 1000 meters per second, around 1 kilometers per second, which should last them around 1 year for this demonstration. I'm sorry, around this demonstration mission there. And if they're going a little bit higher, around if I remember, around where the rocket labs actually going to deploy, should last them around 1 year and 6 months, or aka 18 months for this mission. And you can see cross-section without the propulsion, but with the propulsion, it's just only cross-section without propulsion is 250 centimeters square. I hope I got this right. But cross-section with propulsion would only consumes around 322 centimeters square there. Yeah, pretty good. And yeah, actuators, processor, sensors. Okay, I'm not going to go too long. There's it. Maximum solar power input for the Evercube power system, only 50 watt, operating at 5 volt. but it can actually operate even a little bit more, around 30 volt, if the power, if there's a lot more solar panel being used here. And also thermal management, very important, otherwise it will be super hot. And they are going to use the electric propulsion system, which they will fly with impulsion nano FEEP. Yeah, they didn't specify what is it, but it's going to go a peak thrust of around 350 micronewtons, which should be around, I believe around 35 grams, 35 plus grams of propulsion, something like that. Yeah, correct me if I'm wrong with my calculation, because it sometimes switch to this stuff. So what do I know? Yeah, I believe should be 35 grams. Correct me if I'm wrong. Okay, and I guess that's all. I don't want to be too specific. You can see this plot here, the orbit times, whatever. If you're very interested, I've already linked it in my video description. In the video description, you can actually read this for yourself. The website, there's 6. I've already put it, and also they will have future plans but around this topic. As far as these writings goes, they didn't specify it yet, because they didn't make up their mind. As long as it's still not yet launched, what they can do, they can do nothing at this point. They want to see the data first. Okay, so you can say that even in the worst case scenario, yeah, here you see, yeah, if they said here, if the apogee increased to 1,500 kilometers, the orbit lifetime should be still be under 18 months, 1 year and 6 months. That's actually what I want to mention. But with this orbital parameter around 200 by 1,000 kilometers, it should last them under 1 year, aka 12 months, like that. But since they have a very small cross section around 322 centimeter square, it should be very good for that. So this is what they're going to target for the actual mission. But for now, they will go with 550 kilometers just to test out for 3 months before they finally commission and goes around this one. Okay, so that's all. I'm not going to be too long. Let's go. Okay, so this is how it looks like. Okay, so
requesting your go or no go for launch.
Okay, let's hear from the. Okay, LD is go.
LD on countdown.
All right, launch director is go. LTD is also go. Okay, so what you're looking right now is the visual from live from the Mid-Atlantic Regional Spaceport, just next right into the Wallops Flight Facility,
the weather is tracking green on the
located
eastern
in
shore,
Virginia,
the range is
USA.
clear, and the team is ready for flight. Coming up next in the countdown will be the start of Electron's auto sequence, when the rocket's flight computer takes over operations from T-2 through to liftoff. A couple of seconds after that auto sequence starts, the propellant loading process will complete, and we should hear a call out from mission control that confirms this at around T-1.5 minutes to launch.
All right, so looks like the LOX and also fuel.
By then, we should be within a minute of
Yeah,
Electron's liftoff
LOX
for
and
the
also the
STP-S30
RP1,
mission,
the super
with the rocket
refined
scheduled to light up its
kerosene
engines
on
at
the
2
second
seconds
stage
before
is still
T0 for an
topping up
on-time launch.
until the
back to
confirmation
mission control
from
to
the
listen
T-1
through all of
1
that
minute
final
and 30
count,
seconds,
and we will be back
which
with
right
you
now,
shortly after launch. Go
should be
STP-S30.
around, which by now should be around 1 minute and 40 seconds from now. So we shall see that too. Okay, and also for the new and current viewers, hello and welcome.
And counting. Your 3-word procedure is now in effect. From now on, there should be no red flags in your critical LCCs. Beacon LD on countdown.
All right.
Please lock the auto sequence and confirm.
Auto sequence is locked.
Confirm
Okay.
all flight computer as goes are green.
Alaska is green.
Okay, so
We are
from
go
the
for auto
other...
sequence start at T-minus 2 minutes, and LD is go for launch.
Okay, so looks like 30 seconds from now, the onboard computer inside the Electron rocket will go into the automatic launch sequence, after which at that point it's going to handle most of the complicated task onboard the rockets. Let's say, for example, such as payload, maybe even conditioning, whatever is it, because it's very complicated process after that. And T-minus 2 minutes mark, and right now Electron rocket is in full automated
The
power
vehicle
right
is
now.
fully on internal power.
Okay, and it's
Reception
now,
is nominal.
and,
AFTS is green and enabled for flight.
and usually internal power means that the rocket is now using its own battery inside its own, and no longer relies on external power sources. And getting ready, should be hearing for the propellant load confirm on the second stage. Let's listen in. Okay, but
complete systems in recirc.
all right, and looks like we also kind of confirmed there. The propellant load on the second stage also already complete, and even the first stage already
Anti-gas ring
complete.
is disabled.
And looks like we are getting ready. Arm chain for the ignition on the first stage. T-minus 1 minute 60 seconds before launch. And look, and also, of course, this is my first stream ever for that actually where the launch is actually happening, other than few places that I ever covered before. So that's why I also stream this. T-minus 40 seconds, getting ready for the launch, and getting ready for the T-minus 30 seconds. Get ready on my mark. T-minus 30 seconds, and all of the system is already good to go. So let's getting ready for the launch. T-minus 20,
seconds.
19, 18, 17, 16,
There you go.
15, 14, 13, 12, 11,
10,
10,
9,
9,
8,
8.
7, 6, 5, 4, 3, 2.
Okay, we have ignition of 9 Rutherford rocket engines on the first stage, launch clamp release, and liftoff from the Mid-Atlantic Regional Spaceport on the launch pad 0C, aka known as the Rocket Lab Launch Complex 2. We have liftoff, and here is the visual launches of so far. It's looking pretty good. Okay, this is the view right now. It's looking pretty beautiful on the camera tracking side here.
Beautiful, clean liftoff
Okay,
from
Mach
Rocket Lab Launch Complex 2
0.5.
on the eastern shore.
And by now,
there goes Electron in
all of
full
the 9
flight for the
Rutherford rocket
STP-S30
engines on the first
mission.
stage
We are
should already
T plus
been
45
throttling
seconds
down
past
to
liftoff, and Electron's velocity is
60%
climbing past
before it's
700
going
kilometers an hour,
before going to
now
the
at just past 5 kilometers above Earth.
to this
We are
supersonic.
quickly approaching the moment of maximum
after that,
aerodynamic pressure, otherwise known as max Q, which is when the forces against the rocket are at their peak.
yeah, before approaching to the max Q, which is maximum aerodynamic pressure fully exerted on the launch vehicle according...
Supersonic
Okay,
max Q.
supersonic, getting ready for the max Q. Yeah, here we can hear the sound. Presumably onboard sound on the rocket itself.
Clear max Q.
Okay, already clear the max Q, and now throttling back up
Electron
again
has
to the
cleared max Q
100%.
and is continuing its southeastern trajectory off the coast of Virginia out over the Atlantic Ocean. The first stage's Rutherford engines are at full thrust to take the launch vehicle past 2,000 kilometers an hour, now more
Yeah.
than 23 kilometers above Earth. You can keep an eye on Electron's trajectory with the dials in the top corner of your screen there. That nominal altitude and velocity means we're quickly approaching the next scheduled event for Electron, separation of the stages at approximately T plus 2 minutes and 44 seconds into flight.
Yeah,
What's
so
about to happen
looks
is we'll see
like
the Rutherford
we are
engines
ready.
on the bottom of the first stage
Okay,
throttle
so you
down
can
to
see.
slow Electron just a bit before the engines shut off completely. As you see happening there on your screen, we have main engine cutoff, also known as MECO. The second stage will then separate from the first stage, just a couple of seconds ahead of the engine on stage 2, igniting to continue the mission to orbit. These three events have already started to take place, so we're just going to sit back and watch these happen on our camera lives as we listen into mission control for the callouts.
Okay, and that's what we hear, and hopefully the video balance and also my voice is good. And so far the altitude is 70 kilometers and this velocity is under 7,300 kilometers per hour. And interstage separation after the MECO, the main engine cut off, and we have ignition, SES,
That is
second
MECO,
engine
stage separation,
start.
and second stage engine startup
And
complete
this
on
one is
Electron
the
for
start out of the
STP-S30 mission. A nice
Rutherford
clean set of
vacuum
events
rocket
that
engines
sets us
here.
up for
You
failing
can see.
jettison in under a minute.
Yes, now that we have cleared the lower atmosphere, we jettison Electron's two nose cone halves to drop the excess mass from stage 2, and the
Okay, getting
DiskSats
ready.
get their first taste of space. Just a few seconds away from that fairing jettison taking place, so let's bring back up the mission control comms to listen in and watch along.
Yeah, and getting ready for the payload fairing jettison or separation. We shall see soon. Here you can hear the rocket onboard microphone here picking up the exhaust sound there, even though in space, but it's not truly 100% vacuum space, and looks like we have the payload fairing separation.
Holding nominal.
Should look
Correct,
like it.
jettison confirmed.
Yes, we already confirmed the payload fairing has already
We are
separated.
just about 4 minutes into flight there, and the mission is proceeding nominally as Electron continues to orbit, now at more than 8,200 kilometers an hour, with its altitude at just past 160 kilometers. We've got a couple of minutes before our next event to take place on the second stage, the battery hot swap. This milestone keeps the second stage Rutherford engine burning across its entire engine burn time.
Okay, so like we heard from the commentators, official commentator on Rocket Lab, the battery hot swap will also initiated, where the currently there's actually 4 battery packs surrounding the second stage engine there.
Now, to get to that
The
initial
two sets
550
is still
kilometer target,
it's
the
actually on the
second-stage
way
Rutherford engine on your
using it.
screen has an engine burn
And after
time
that, the
just
hot
shy of
swap, what
7 minutes
what it
before
will
the kick
tries
stage
to
is
do is that
separated
it's
and
going
sent
to
on its way with the
use
DiskSats.
it will
To keep
simultaneously
the
going to
engine
use
burning
the
for the
another
duration,
two
we need to
unused
swap out the batteries that are
battery
powering the
pack,
engine's
and
fuel
it will
pumps. They
simultaneously
end up
eject
becoming
the
fully depleted
used
after about
already
4 minutes
used
of
expanded
use. So before we run out,
battery
Electron
pack.
performs a battery hot swap to
It
switch
will
to a new
jettison
battery pack
to
that keeps the
to
engine
ensure
running.
to
We'll hear
ensure
few callouts
the
from mission
rocket
control
engines
in the lead up
running
to that
running,
moment.
and also to keep the
HVD discharge
mass
holding nominal
of
refers to
total
the
mass
high
of the
voltage batteries that are currently
of
in
the
use,
launch
with the
vehicle
operator
keeps
letting us know that those batteries
keep
are
it down so
performing
it
as
can
they should
actually reach
for
to the
another
orbit
reminder about 30 seconds before the actual hot
better
swap.
and faster
And when that hot swap
than
happens,
if it's
you should
still
see the
keep
silver
that
battery packs on
that
your screen
weight inside
disconnect and disappear, which will be
inside
our
and
visual
also
confirmation that all was
at the side
nominal
of
with
it.
that event.
So
Hot
so that's
swap
why
is
it's
scheduled
very
to occur
important.
in approximately T plus 6
Oh,
minutes,
and
40
apparently
seconds,
looking
so
from
let's listen in
uh,
and watch out for it now.
so looking like on this, it's pretty funny. They're actually also using their own
Guidance is nominal, 200 seconds
capture,
remaining.
just like how I'm using with my stream stuff. I guess that's what's happening in the digital streaming, digital broadcasting era right now. So that's it. It's pretty common, and altitude is 250 kilometers, and the velocity speed is 12,500 kilometers per hour and counting up. And of course, because it's in space, even though it's not 100% fully in space, that's why you can hear, okay, it's already throttling down, should be around 80 or maybe 60% to keep the acceleration under 3 Gs or 5 Gs. Yeah, to ensure it doesn't accelerate too much that it could destroy us. And you can see the battery has already jettisoned. Two batteries already being
And with that, we've
separated,
completed
and
the hot
another
swap
2
maneuver
is now
for
in
Electron's
use
second stage, with
in
the
this flight
Rutherford
right
engine
now.
continuing to burn bright and nominal on its way for the next staging event. We're clocking more than 14,700 kilometers an hour as Electron continues to climb above 275 kilometers in altitude. We are right on target to deliver the STP-S30 mission to its nominal transfer orbit ahead of payload deployment to our 550-kilometer LEO destination. Once they're deployed, the 4 DiskSats will operate in pairs. One pair will remain at 550 kilometers above Earth to test out operations at that altitude, while the other pair will maneuver into what's known as Very Low Earth Orbit, or VLEO, which is considered to be between 300 and 450 kilometers above Earth.
All right, well, coming up next will be the second stage engine cutoff, or SECO. This manoeuvre follows relatively the same procedure as main engine cutoff, where the Rutherford engine on the second stage will shut off ahead of the final separation of the vehicle between the second stage and the kick stage. There will be a bit of a gap between that final separation and payload deployment, as the stage separation places the kick stage in an elliptical orbit of Earth first. So we'll explain what happens then after we receive confirmation from Mission Control, first of SECO and then stage separation.
Okay, so that's what we have heard from the explanation, and velocities is 20,000 kilometers per hour, and the altitude is almost 297 kilometers altitude already. Okay, already now, and counting up. And of course, because even though you are in space right now, you need to remember it's not 100% fully vacuum. Okay, because remember there's particles and also gas still interacting around the space, and especially if you know about astrophysics, you know pretty well it's not 100% fully vacuum. So that's why we still can hear the onboard microphone sound of these rocket engines there. That's why you can hear it. And of course, because it's using super refined kerosene, the RP1 rocket propellant 1, of course that's why it's colored like this, pretty orange color there, with a little bit slight on the tail end of the exhaust. You can see a little bit of blue side there, and we have, and looks like we have SECO, second engine cut off, and then
there we have
nominal
second
orbit
engine cutoff
insertion already confirmed,
and
then now the kick stage, the Curie upper stage has already separated, and now is in and right now it is in the
what that means is that
ballistic course phase. Basically, the engine,
orbit. Once it connects the dots on the other side, the kick stage's Curie engine will fire up to circularize its trajectory at a 550-kilometer altitude before payload deployment can begin one by one for the 4 DiskSats on board.
We're going to leave you with this tracking graphic of the kick stage's trajectory to keep an eye on where it is, but take a break, stretch your legs, and we'll be back with you just before payload deployment begins for STP-S30. We'll see you back here soon.
Okay. So that's what we have heard so far, and yeah, and you need to, and I need to also tell you that because it's in space, and also if you see the rocket exhaust plume, it's getting bigger and bigger. It's because it's already going up to a certain atmospheric layer that the atmospheric pressure itself cannot how do I say it can no longer keeps the shape of the exhaust plume intact inside the rocket nozzle itself. So to solve this problem, usually what they are doing, usually what every aerospace company out there do is that they take this base sea level nozzles that's pretty short there. They lengthen it up to some degrees, could be up until around, if I remember, up until around 20 by 1 nozzle exit throat design, just to handle all of this stuff. Sometimes they can even go higher, around hundreds if they want to, just to optimize it, and of course to minimize the thrust loss, and also enhancing the efficiency that the rockets can deliver if they go with such design. But also there's another alternative how to do this without expanding the rocket nozzles. One of it is to actually change it into best example would be to change it into into aerospike rocket engines, where you still can keep the design like that. You don't have to expand anything. It's like something like aerospike. Yeah, the aerospike nozzle design like there, like that. On the spike area, technically, if you want to save weight, you can actually cut it half. And there's also some additional bonuses by using that. If you design it properly by cutting it down, and then maybe you want to send it a little bit so it looks like how do I say, like some half empty, half hole inside on the middle of the aerospike there. Technically, you can also enhance the thrust level of it and whatnot, because you are also using the free sort of like a free heat, free pressure from the exhaust itself to actually pushes it up and sort of give it like a free boost on board of the engine. So technically, you can also achieve that stuff, but the problem is that cooling and also the material needed to actually construct one. And so far, from my knowledge, there isn't any active aerospace company out there that actually put this into demonstrate beyond the ground level demonstration. Not yet going with in real life flight so far, but one can hope. Nothing can stop a lot of very enthusiastic people out there, and also especially some highly coordinated team with even whatever budget they can do to also do it. You never underestimate this kind of enthusiasm, especially rocket and spaceflight nerds like me. You don't underestimate it because that thing can happen, but one day, one can hope. So this is it. It's currently costing into the flight, and since I've already mentioned before about the paper itself, so I don't think I need to cover a lot. Even if I try to cover it, it's going to be highly interesting for you, and it's also going to be too tiring for me to just keep talking about such topic, right? Because yeah, at the end of the day, I'm just a human. just like to rest also sometimes, but for now, I'm going to leave you guys with the visual for now. So see ya around T plus. I don't know. Let me see at what T plus there. because it's still actually costing around. Okay. Okay. So I've already put my notice here. So yeah, here you go. Oh, how I'm going to do this? This is a bit painful. Okay, already done. Should be okay, isn't it? Okay. Yeah. So yeah, everybody, I'm taking a bit of break. Maybe I'll take a little bit of nap, and then but until then, I'll just have a little bit of rest. It's pretty busy, and also I'm kinda sick right now. If you even hear my voice change, that's the reason why. So thank you, everybody. Thank you for your understanding. I will be back again soon, sooner than later. So yeah, see ya. We'll be back again.
Hello and welcome back to the launch of Don't Be Such a Square. We're just moments away from beginning payload deployment of the 4 DiskSat satellites for the STP-S30 mission. Earlier today, bright and early from the eastern shore of Virginia, we launched our 78th Electron rocket from Launch Complex 2 at 12:03 a.m. local time, with a clean ascent through the usual milestones, including max Q, MECO, stage separation, and second stage startup. After Electron's stage burn was complete, its engine also shut down and separated the kick stage from stage 2. The kick stage was then released into a transfer orbit on an elliptical trajectory with the STP-S30 payload.
That coast journey around
Hello,
Earth
everybody,
has now been
and welcome
completed,
back in.
and the Curie engine on the kick stage has just finished its
yeah.
1 minute and 46-second engine burn, repositioning to a circular trajectory in low Earth orbit. That brings us just seconds away from the deployment of the first DiskSat on board,
Alright.
and we're standing by to listen
yeah.
out for confirmation from mission control.
So let's go. Let's hear the confirmation for the DiskSat. We might see the first will separate, and then later on second, third, and fourth. We'll see on this flight. So here we go. This one is the animation. Slight delay from the actual event, but otherwise should be fine. Okay. I'm getting ready. Okay, here we go. Should be on the first one of four DiskSat already.
DiskSat 1, payload deployment confirmed.
Okay, the DiskSat number 1 has already separated. Getting ready for the number 2. And the letter number
Great
3
news from
and
Mission
number
Control. That is payload deployment confirmed for the first of 4 of today's satellites and the official debut of DiskSat in space for the very first time.
4. Yeah.
Each DiskSat is being deployed one at a time with a couple of minutes of spacing in between to ensure a safe operational distance. With the first one gone, we're scheduled to deploy the second one at T plus 1 hour, 2 minutes, and 30 seconds.
Okay, it's not going to be that long. It should be around 2 minutes. Getting ready. Mark 2 minutes. 2 minutes left before the payload. Before the DiskSat number 2 will be separated soon. And this separation gap actually happens because to give the satellites more time to space out in between of the other satellites. Otherwise, if it goes way too fast, it will also going to hit the other satellites and could cause damage, or even worse, could be another Kessler syndrome on the way. And you need to know, because the space is pretty. Because going to orbit requires a tremendous amount of energy and velocities. Of course, even the smallest as hairpin, or maybe even a needle, it's going to damage a lot of the satellite. That's why they have to space it in between. Okay, and 1 minute left before the separation of the DiskSat number 2 out of 4 total DiskSats in this flight.
We are approaching the timed payload deployment for DiskSat number 2 in roughly 40 seconds. Like before, we're expecting to hear the call out from our operator in mission control that confirms that separation event has taken place. Let's listen out for it now.
Yeah, so let's get ready. Okay, should be okay.
DiskSat 2, payload deployment confirmed.
Alright, so looks like the DiskSat number 2 has already separated. So 2 left.
Congratulations to the team on payload deployment number 2 for the STP-S30 mission. 2 down, 2 more to go to close out this
so
mission.
here's the
We've got DiskSat
animation,
scheduled
how
to
it looks
deploy
like.
in about 2.5 minutes at T
Slight
plus
few
1
seconds
hour,
of
5
delay,
minutes and 16
as
seconds.
we can see.
So, same as before, we're standing by for a couple of minutes until we come up on that third deployment event. Stick with us.
Okay, another few couples of minutes left, so we still have time. I'll go a little bit taking a bit of short break. So yeah, we'll be back again.
All right, it is almost time to deploy DiskSat number 3 from the kick stage. Just 30 seconds or so remaining until that third satellite is triggered for release from its dispenser to join the first 2 satellites already deployed. Let's listen in.
Alright, so getting ready for the DiskSat number 3 to be separated from the payload dispenser too. So we'll see. And yeah, for new and also existing current viewers, hello and welcome to this stream. You are now watching the live of the launch and also deployment of the DiskSat mission for the STP-S30.
Expected DiskSat 3 payload deployment.
Okay, getting ready. That one is the live, not really live, it's more like
Nice
a
one from Mission
real-time.
Control. That is 3 for 3 so far for the STP-S30 mission, with just one more
Okay.
DiskSat to go. That one is roughly scheduled for deployment at about T plus 1 hour, 8 minutes, and 16 seconds. So not long to go now to complete this constellation of DiskSats on orbit.
Okay,
Launch danger area has been removed. Access controls are back to the fence line.
Copy, GSO.
alright, so that's what
These are
we are
welcomes.
hearing. Okay.
Thank you, sir, for your support there, GSO.
Okay, so that's what we hear right now. The DiskSat number 3 apparently already separated according to the mission control. And at T plus 8 minutes and 16 seconds, we're going to see soon. Okay, around 2 minutes from now, getting ready. Mark 2 minutes from now before the DiskSat number 4 separation and fully deployment of this. So we are going to see that soon. So that's why I said you are now watching the live, not only the launch of the Electron rocket, but also the deployment of the STP-S30 mission. The stands for Space Test Program S30. For the DiskSat for the satellite technology demonstration mission. That's basically making it a quasi two-dimensional, or aka 2.5D satellites here. So they are going to test out around the first around the low Earth orbit region, just to test the satellites before eventually they will pull this down the perigee to 200 kilometers by the apogee of
Okay, the moment is
1,000
here.
kilometers,
The final payload deployment event
for
to release
full
DiskSat
test
number
after
4 to orbit
after
and
three
complete the
three
launch
months
for
of
STP-S30.
deployment and
We are
commissioning
just a few
test
seconds away now.
after that.
So for one last time, let's bring up the audio from Mission Control and listen in for that final payload deployment from the kick stage.
Okay, and also you need to know this mission is also collaboration between the United States Space Force (USSF) and also NASA, National Aeronautics and Space Administration. So that's what we are going to see. And the,
DiskSat 4 expected payload deployment.
okay, getting ready for the DiskSat number 4 to be deployed. And this mission name is actually Don't Be Such a Square.
Congratulations
Oh.
to the STP-S30
Okay.
mission operators. That is payload deployment confirmed for the 4th.
Okay,
and
so
final
looks
DiskSat from
looks
the
like
fifth stage,
already
and
full
mission
deployment
success for
of it.
Electron's 20th launch
So
of the year.
congratulations
All the very best
um,
with on-orbit
to
operations
Rocket Lab
this
for successful
exciting
launch,
technology
and also
demonstration
congratulations
the
for
Space Test
USSF,
Program,
United States
Aerospace
Space Force, and
and
also NASA,
Congratulations
National
as well to the
National
organizations
Aeronautics
involved in
and
the launch
Space
across the
Administration for
SSC system
successful
Delta 89 capability
launch and
development
payload
branch
deployment of
and the
this.
Rocket
So
Systems
looks
Launch
like
Program.
they have to test this for 3
Launching
months
this mission
before
to
finally
orbit 5
fully
months
going
ahead of
for the
schedule is a
full
fantastic
operational
feat,
site,
backed by
where they are
great
going to go
partnerships.
with
And we
the
are
very
proud
low
to
Earth
have
orbit,
delivered mission
VLEO,
success once again
and
that
then
serves
also
the
to change
technology
the
advancement needs for the nation.
latitude.
And
Okay,
congratulations,
2 pairs,
of course,
another
to
2
the
pairs
Rocket
for
Lab build,
for
test, and launch
altitude,
teams
another
on
2
yet
pairs also
another
for
launch
the
this
latitude.
week.
So
Let's
that's
do
it.
it all again, one more time, for our 3rd launch in 7 days, coming up this weekend to round out the year. You can look out for more information about that mission on Rocket Lab's website and social
Okay,
media
so
channels.
from what we can
Otherwise,
hear, it
we'll see you
means
back here soon for yet another Rocket Lab launch. This is
another
Rocket Lab
launches
Mission
will be
Control, signing off.
around 27th of December 2025, or should be around maybe Sunday. Yeah, around Sunday. But if that's not it, it could be also 26th of December, around Saturday. But if it's streamed around the time, how do I say, around the time where it's still not yet sundown, so I might not be able to stream if it's on Saturday. Otherwise, if it's around the night, yes, I will try to do it. So thank you so much, everybody, for watching. And also, just like what this Rocket Lab coverage says here, thanks for watching today's live coverage. And yeah, of course, if you need real-time updates, you can also visit their Twitter/X social media site here at Rocket Lab. So that's it. Thank you so much, everybody, for watching. That's a very, very successful launch of the Electron rocket from Mid-Atlantic Regional Spaceport, just next to the Wallops flight facility. So that's what we already looking so far, and successful launch and also successful deployment of all of these 4 DiskSat satellites. Just to speak a bit bluntly here, I guess. But that's it, everybody. Thank you so much for watching. We see you on the next stream whenever I can, and because of my how do I say, my current health right now, it's not really the best so far. So I'll see you around whenever I can, and also don't forget, if you need to know the timetable, schedule, and whatnot for the launches, just head over to the Next Spaceflight app, or you can also use the website nextspaceflight.com to also that one is actually maintained by NASA Spaceflight. Okay, so you can check it out. If I can stream it or not, you might see it on the on my channel. But otherwise, that's it. No stream at that time. So thank you so much, everybody, for watching. Okay, so this is my closing trademark. So thank you, everyone, for watching, and I'm Daniel Suguwa, your host for today's launches. So thank you, everybody, and take care. Goodbye, and see you soon. Take care. And that's it. Nothing else in behind the scene. It's already finished. What else do you need to know? So yeah, that's it. I'm not going to cut myself out. So I'm going to count this: 5, 4, 3, 2, 1. So that's it, everybody. See ya.